Let's say that we have a first order differential equation and we're trying to solve for y as a function of t. And let's say that our equation holds the form the derivative of y with respect to t is equal to some function of t and y, and we will call it f of t and y. And if we can algebraically manipulate this equation in such a way that it becomes the derivative of y with respect to t is equal to some function of the ratio y over t, and we can call this function capital F. And so if the equation can be expressed in this form, then we can refer to this equation as a first order homogeneous differential equation. And the first step of solving such an equation is to use substitution. So we can say that v of t is equal to y over t. And then we can rewrite this and say that y is equal to v times t, and then we can differentiate this. But when we're taking the derivative of y with respect to t, because v is also a function of t, then we would have to use the product rule on the right side. So that would be v plus t times the derivative of v with respect to t. So next we just have to complete the substitution by plugging in these values back into the equation. And so we said that the derivative of y with respect to t is this term v plus t times the derivative of v with respect to t. And that will be equal to the function that we called capital F of v, because we said that v is equal to y over t. And as you may have noticed, this is actually a separable differential equation in terms of the function v. And if you're not familiar with separable differential equations, I suggest you watch the third video in our differential equation playlist. I will leave the link in the description. And so we will start separating by subtracting v from both sides, and that will give us t times the derivative of v with respect to t is equal to f of v minus v. And finally, after we complete separating the t's from the v's, we get on the left side 1 over f of v minus v times dv is equal to 1 over t dt. And so we can integrate this and then back substitute for y and solve for y. So let's make things more concrete by solving this initial value problem. So before we can start the substitution process, we first must make sure that this equation is in the correct form. And to do that, we can start by dividing the entire equation by t squared. And so when we do that, we get y over t times the derivative of y with respect to t. And we can use the Leibniz notation here, plus 4 plus y over t squared. And all of that will be equal to 0. And then when we subtract these two terms from both sides, we get y over t times the derivative of y with respect to t is equal to negative 4 minus y over t squared. Now at this point, the equation is not exactly in the form as we have it here, but wherever y and t appear in this equation, they appear as the ratio y over t. So we can actually start the substitution process at this point. So if we say that v of t is equal to y over t, and we can rewrite that as y is equal to v times t. And when we differentiate this, because v is a function of t, we will use the product rule on the right side. So we would get v plus t times the derivative of v with respect to t. And so when we complete the substitution, our equation becomes v times v plus t times the derivative of v with respect to t is equal to negative 4 minus v squared. So now that we have our equation in terms of v, we can start the separation process. So we can distribute this v on the left side, and we get v squared plus v times t times the derivative of v with respect to t. And that will be equal to negative 4 minus v squared. And so when we subtract v squared from both sides, we get v times t times the derivative of v with respect to t is equal to negative 4 minus 2 times v squared. And we can divide the v from both sides, and we get t times the derivative of v with respect to t is equal to negative 4 minus 2v squared over v, which is actually, if we want to factor out negative 1, we can say negative times 4 plus 2v squared over v. And finally, when we complete the separation, on the left side we get v over 4 plus 2v squared dv is equal to negative 1 over t dt. So now that we have our equations separated, we can integrate both sides. And when we do that, we get 1/4 times the natural log of 4 plus 2v squared. And on the right side, we get negative natural log of t plus the constant of integration, which could be rewritten as the natural log of 4 plus 2v squared to the 1/4 is equal to natural log of t raised to negative 1 plus the constant of integration. And then when we exponentiate both sides, we get on the left side just 4 plus 2v squared raised to 1/4, and on the right side we would get e raised to the power of c times e raised to the natural log of t to the negative 1. And because c is an unknown constant, e raised to the power of c is also an unknown constant, so we can refer to that as c. And e and the natural log cancel out, so you're left with c times t raised to the power of negative 1, which is the same thing as c over t. So to solve for v, we can start by raising both sides to the power of 4. And when we do that, the left side becomes 4 plus 2v squared, and on the right side it will be equal to c raised to the power of 4 over t raised to the power of 4. But again, because c is an unknown constant, this is also c to the fourth is also an unknown constant, so it can be absorbed into the constant. So that will be c over t to the fourth. And then when we subtract 4 from both sides, we get 2v squared is equal to c over t to the fourth minus 4. And then when we divide 2 from both sides, we get v squared is equal to 1/2 times c over t to the fourth minus 4. That could actually be rewritten as v squared is equal to 1/2 times c minus 4 times t to the fourth over t to the fourth. At this point, we can actually back substitute and make this in terms of y. Remember that we said v was equal to y over t. So when we back substitute, our equation now becomes y over t squared, which is the same thing as y squared over t squared, is equal to 1/2 times c minus 4t to the fourth over t to the fourth. And to solve for y, we will multiply t squared to both sides, and we will get y squared is equal to 1/2 times t squared times c minus 4t to the fourth over t to the fourth, which can be simplified as y squared is equal to c minus 4t to the fourth over 2 times t squared. So now that we have the equation back in terms of y, at this point we can actually plug the value of the initial condition to solve for the unknown constant c. So when we do that, we get -7 squared is equal to c minus 4 times 2 to the fourth over 2 times 2 squared, which is 49, is equal to c minus 64 over 8. And when we multiply 8 to both sides, we get 392 is equal to c minus 64. Finally, when we add 64 to both sides, we get c is equal to 456. So now that we know what this unknown constant is, we can plug it back into the equation and get the particular solution. And so when we do that, we get y squared is equal to 456 minus 4 times t to the fourth over 2 times t squared, which is equal to y squared is equal to 228 minus 2t to the fourth over t squared. And then when we take the square root of both sides, we get y is equal to plus or minus the square root of 228 minus 2t to the fourth over t squared. At this point, to figure out which sign between the plus or minus is the correct one for our particular solution, we can plug in the value of our initial condition to figure it out. And so when we do that, we get -7 is equal to plus or minus the square root of 228 minus 2 times 2 to the fourth over 2 squared, which is the same thing as plus or minus the square root of 196 over 4, which is the same thing as plus or minus the square root of 49, which is plus or minus 7. So the correct sign for our particular solution is minus. So finally, our solution is y is equal to minus the square root of 228 minus 2t raised to the fourth over t squared. And this is the particular solution that satisfies our initial condition.